Since we don't have the authors here to ask questions, please do reach out to them via email if you have any. But we'll be moving on to the third and final presentation here, which is on IRRedicator, Pruning IRR with RPKI-Valid BGP insights. So yeah, we got the slides, so I think you're good to go.
Okay, thank you. Hello everyone, I'm Min-hyuk Kang from Seoul National University, and I'm very delighted to have the opportunity to present our collaborative research, IRRedicator, Pruning IRR with RPKI-Valid BGP insights. So, to give you a better understanding about our research, I would like to start with some background about the Border Gateway Protocol. BGP is one of the most crucial components for maintaining global internet connectivity, acting as the foundation for routing information exchange and the creation of routing tables. And originally, BGP was designed without security measures. Specifically, BGP has no route origin authentication mechanism, so anyone can theoretically announce any IP space. So this makes BGP vulnerable to routing errors made by network operators, and attackers have exploited this weakness by announcing someone else's IP address space. So, for example, in 2012, a route leaked by an Indonesian ISP unintentionally disrupted Google's services for 30 minutes. And if you think that only happened in 2012, that's not the case. It is actually still happening. So for instance, in 2022, hackers had stolen roughly $1.9 million from the cryptocurrency platform by launching a prefix hijacking attack. And these BGP incidents happened again and again, demonstrating how severe the impacts are, ranging from paralyzing services of tech giants like Google to cryptocurrency stealing. So, substantial efforts have been made in order to improve the BGP security. In 1995, the Internet Routing Registry was established to mitigate routing errors and attacks. And it is widely adopted for sharing global routing information. For example, 68% of ASes have published their IRR objects, such as route objects. However, the IRR lacks an authentication mechanism, and some of its entries could be outdated. So the Resource Public Key Infrastructure, RPKI, was introduced in 2008 to overcome the limitations in IRR. And RPKI provides a way to cryptographically bind an IP prefix to its legitimate origin AS with route origin authorization object, ROA object. So it has been rapidly deployed, but it also has some challenges such as the certification dependencies in the hierarchy of RPKI and some misconfigured ROAs. So right now, RPKI has a relatively narrower coverage than IRR due to the complexity involved in registering and managing RPKI objects. But IRR and RPKI, both IRR and RPKI have its own pros and cons. They can complement each other. So we aim to take advantage of the strengths of both databases in order to improve the BGP security. And here I will briefly explain the data sets used in our paper. And when analyzing RPKI, we use ROAs fetched from the RPKI repositories. And for IRR, we use two data sets, RADB and all IRRs. And the latter is a superset. RADB data sets consist of route objects downloaded only from the single IRR database, which is RADB, and all IRR's data set also contains the route object in RADB, but it additionally contains the other route objects registered in IRR databases operated by the 5 regional internet registries. And hereafter, I will use the term IRR to refer to the all IRR's dataset. And first, to understand how they are used in practice, we analyzed historical data of IRR and RPKI objects and their coverages of BGP announcements. And we found that over 93% of BGP announcements are covered by IRR, whereas 40% of BGP announcements are covered by RPKI. And among these covered BGP announcements, we analyzed the percentage of BGP announcements that are valid against IRR and RPKI respectively. And here, a BGP announcement is considered valid if the origin AS of the BGP announcement is the same as that of the corresponding objects in IRR or RPKI. And we found that over 98% of BGP announcements are valid against RPKI, whereas 90% of covered BGP announcements are valid against IRR. So there's a gap between the percentages of valid BGP announcements between IRR and RPKI, which might imply the inconsistency between them. So to answer whether there are any inconsistencies, we compare the origin ASes of the prefixes registered in both databases. And we found that over 60,000 IP prefixes in IRR are registered with the origin ASes that are different from those in RPKI. And another interesting finding is that over 20,000 BGP announcements are covered by these inconsistent IP prefixes. And this means that the validation results of these BGP announcements can be different against IRR and RPKI. And so we need to address these inconsistencies for a more reliable and secure routing infrastructure. So to handle this problem, we further examined whether these inconsistent IRR objects exhibit any specific characteristics that can differentiate them from the consistent ones. So someone might say that we can take a look at the age and filter out some outdated objects. And of course, intuitively, the older IRR objects can be more likely to be stale than newer ones. For example, the 90th percentile age of consistent ones is 10.8 years, in contrast to 16.3 years for inconsistent ones. And this led JPIRR to implement a policy to remove IRR objects that have been unmodified for over a year. However, using the age as a sole criterion to identify inconsistent IRR objects would not be sufficient. For instance, let's assume that we remove IRR objects that are older than the 90th percentile age of inconsistent ones. This removes 10% of inconsistent IRR objects, but it also eliminates about 1.6% of consistent objects, which indicates the need for more fine-grained approach. Then, how can we deal with inconsistency between IRR and RPKI? As we saw in the previous example, the age-based filtering is not sufficient, and setting a reasonable threshold would be challenging. For instance, if you use a high threshold, then only a small fraction of inconsistent entries would be filtered. On the other hand, if you use a low threshold value, then some valid entries could also be eliminated. So what else we can do? Another straightforward approach is to filter out inconsistent IRR objects using RPKI. But RPKI only covers about 44% of IRR objects, so we came up with an idea of using external information in addition to RPKI. That is, we leverage temporal patterns of BGP announcements to identify inconsistent IRR objects. And this can be applied to all IRR objects, including the ones that are not covered by RPKI. So to do that, we introduced 3 metrics to assess the BGP announcement patterns, namely lifespan, uptime, and relative uptime, and each of which is calculated within a monitoring window. The monitoring window spans from the chosen start time t to the latest date of our data set, and the lifespan is the time period in days that from the first observation of the corresponding BGP announcement to the last, divided by a monitoring window size. And the uptime is the number of days that the corresponding BGP announcements have been observed, divided by a monitoring window size. And the relative uptime is the uptime divided by the lifespan. And we measure these three metrics across 20 different monitoring windows. And this figure shows the average results. And we found that there are noticeable patterns in BGP announcements to distinguish consistent and inconsistent objects. Interestingly, consistent objects exhibit higher scores in all three metrics than inconsistent ones. And this indicates that consistent objects tend to be more recently and steadily used, and they tend to be more frequently announced in BGP than inconsistent ones. Also, the relative uptimes of inconsistent ones tend to increase as the size of monitoring windows extends. And they get closer to the scores of consistent ones, and this indicates that inconsistent objects used to be actively announced, but they become no longer announced in BGP. So these distinctive BGP announcement patterns have motivated us to propose IRRedicator, which is an ML-driven approach to identify inconsistent IRR objects by leveraging these BGP announcement patterns. So we extracted more than 300 features from our BGP announcement dataset. In a nutshell, we use three metrics: lifespan, uptime, relative uptime, to measure the BGP announcement pattern. And we additionally defined the number of ups and downs and active and inactive days metrics to characterize the dynamics of BGP announcements. And we apply these metrics to our BGP announcements dataset with 20 different monitoring windows. And we employ a machine learning technique to capture the characteristics of BGP announcements. And specifically, we examined 10 different ML models, and the best model turned out to be LightGBM, which is a tree-based gradient boosting model. And we also incorporated a classification with rejection technique into our model to reduce false negatives. And this technique prevents our classification model from making wrong predictions when it is not sufficiently confident. And to evaluate the performance of our model, we utilize two ground truths for labeling. First, we use ROAs in RPKI, which bind IP prefixes to origin ASes. And second, we use transfer logs. The ownership of IP prefixes can be transferred between organizations, and such transfers are logged by the regional internet registries, IRRs, and we use these ground truths to determine whether the IRR objects are aligned with the current ownership status as recorded in RPKI and transfer logs. And this figure shows the result, and our model achieves a high performance, and it performs well across a wide range of threshold value. And this implies that our metrics are effective in capturing the characteristics of BGP announcements. And we further compared the quality of the IRR datasets after applying different filtering approaches. And IRRML is our approach that filters IRR objects using our ML model, and IRRD4 is an approach that filters IRR objects using RPKI only. And we also measure the quality of the original IRR dataset as a baseline. And we compare the quality with the 4 different criteria. First, we compare the number of total entries that remain after filtering, and our approach successfully filtered out about 59% of IRR objects in the original IRR dataset. And by filtering out those stale IRR objects using our method, the percentage of IRR objects that are actively used in BGP increases by 32 percentage points, reaching 60%. And we also measure the percentage of BGP announcements that are covered by each dataset. And our approach maintains a coverage of 88% of BGP announcements. And last, we also measure the percentage of BGP announcements that are valid against each dataset. And 94% of BGP announcements are valid against our approach. And note that after applying our method, the percentage of valid BGP announcements slightly increases since our technique effectively filters out stale IRR objects. So here I will briefly discuss about our approach and future work. The question could come up regarding the aspects who be in charge of applying our technique. And another concern relates to false negatives. While we made efforts to minimize false negatives, there is still a chance that some valid entries could be marked as invalid. So one possible solution to further reduce false negatives would be extending our model to select the single most up-to-date IRR object for each IP prefix instead of making predictions for each IRR object. And so handling these concerns will be the future works. And I would like to mention that our source code and data sets are publicly available via this link. And to conclude this presentation, we conducted a longitudinal study of the inconsistency between IRR and RPKI, and we found that the number of inconsistent IRR objects increases. And second, we analyzed the characteristics of the inconsistent IRR objects, and we were able to capture the distinct BGP announcement patterns between consistent and inconsistent ones. And last, we proposed an ML-based IRR pruning technique, which successfully filters out stale IRR objects. And so if you're interested in learning more about our research, please refer to our paper and our website. And thank you for listening to my talk, and I'm open to any questions.
Thank you. Any questions? If you could state your name and affiliation, that would be great.
Sure. Niklas Vogel from Goethe University Frankfurt. What is your insight? Do you think that with a continuous deployment of RPKI that the IRR will become unnecessary, or do you think both of these technologies will continue to exist even with potential full RPKI deployment?
I think the latter will be, both database will be continuously exist since even after the RPKI is deployed 100%, there is still a chance that some, considering the dynamics of BGP announcement and the change of IP prefixes, the ownership of IP prefixes, if some ASes newly allocated some IP prefix, but they didn't register any RPKI object, then IRR can be used as a complementary data set. So,
okay, thank you. And maybe a follow-up question. Not sure if that's in the scope of your research, but do you know how many systems use IRR information like strictly in routing decisions? So basically filter out routing decisions or routing announcements which are invalid according to the IRR?
I missed your question. Could you
the question is, do you know how many systems actually use IRR information strictly to filter out announcements? For example, if you have an entry which is conflicting a BGP announcement, how many would filter that out?
So your question is, how many ASes are using IRR to filter BGP announcement?
Exactly, yeah.
I know that about 68% of ASes publish the IRR object, but I don't know exact percent of how many of them are actually using the IRR object.
Yeah, okay, thank you.
Any other questions? If not, I have a question. So you've got this ML model that you guys have put together for determining, what's a stale IRR entry and so forth.
Yeah.
Did you explore the use of like explainable AI models at all here? Like, it seems that the operator community is notoriously, shall we say, skittish about applying techniques to their mission-critical networks. Seems like explainable AI might help with that.
Yeah, thank you for a good question, and that is one of our consideration to select the candidate model. We mainly choose the tree-based model and tree-based ensemble model since they have good explainable AI techniques to apply to them. So we can apply, for example, shuffle analysis or counterfactual explanation technique to our model. So that could be.
Okay, thank you. Seeing no other questions, let's thank the speaker again.